small devices, because in these applications you do not have all the power, the memory, and also maybe internet to have cloud access. So that is really the reason why we have to make it on the tiny devices themselves. So the gap that we have to fill is actually there. So you see in the cloud, we have a lot of memory in terms of in the ranges of gigabytes for the activations, the ones that we have to generate for every image. And also we have terabytes of that memory for the storage of the weights themselves. For mobile phones or other devices like this, we have even fewer resources. But even now on the very tiny ones, we have actually not even GBs, we have kilobytes of memory and maybe a megabytes of that for the storage of weights. So then how to fit these models into this? You can see the gap is quite huge, and that is why it's very challenging. So for example, in this case, we have simply two things, three needs for storage. We have the input activation, that is the image that you provide, normally stored in an extra memory. And then the kernel, which is the weights, which we can always be read from the external memory, which is in this case super flash or DRAM. And then once we have this computation, we have to store some activations. And then we usually have to store it on the chip. So, and when you look at the devices we are talking about, they have extra kilobytes and a flash of maybe 1 megabytes. And of course, we saw that these models are in actually a lot of megabytes. So this is why the method that has been presented, the tiny or the neural architecture search, was actually used in this example to design a neural network that is very small to be able to fit into 320 kilobytes of memory. So they call this their first iteration. Actually, they were able to reduce the model size so that it could fit into such a small space. But again, one problem that they noticed that the activations actually, even if you reduce the architecture, you optimize the architecture, then usually activations are still a challenge. So then they further use now this tiny, they call it now, and they refine the space, such space to come up with this tiny NAS. So this is a neural architecture such that it's in two stages. First, they craft the space as we saw, but now including the memory and the storage constants into the space. And then they were able to derive these parameters that were able to fit into this device. So they performed maybe a benchmark on visual words data set. This is where you just model are able to detect some either person or building, such a thing. And then they were able to fit this into a microcontroller. So one of the things they also noticed that because images can be large, you can process it in batches. So you have an image, for example, break it into smaller images so that then you can process in batches. So in hardware, that is really how we enable that, because if you have a big image that cannot fit on the hardware, then you can break the image into batches that then can be processed one by one. And then you combine the results at the end of the iteration. So beyond now the software optimization, I just wanted to show some of the hardware optimizations that we perform to enable this inference on the hardware. So in neural networks, we usually have a nest of loops to iterate over in terms of computation. So when you have a convolution, just a nested loop, for loop of around 7 loops to move across channels, across input channels, output channels, and the filter itself. So these loops can be optimized in order to ensure proper and efficient running. So we have loop reordering that actually tries to make data that is required on memory locally, so that you use it until you reuse it until it's needed no more. Then you read another set of another set of inputs. And then the other technique is loop tiling, which involves just as I said, you can partition this data into smaller loops, so that then you can access this smaller data first and then proceed to the next. The other method is loop unrolling, so where you now enforce parallelism. So rather than processing one pixel at a time, you can process 4 at a go, and then this makes it faster, and then so you iterate less. The other technique is single instruction multiple data. So you can actually give one instruction. This is supported in some of the hardware, and then you do multiple operations on the same data, or use multiple data on the same instruction. So of course, there's other support, the other hardware that can support multi-threading, such that you can process several operations in parallel. So to look at them just briefly, some of them is that, for example, loop reordering. So if you have two tensors, for example, it matters which order you process this computation. Because if you have this, in hardware, we have all the data contiguous in memory. It's all laid out as one single stream of data. So how you access it matters, because if you keep using a very irregular pattern in access, that takes a lot of time to retrieve the data. So then if you reorder your loops appropriately in hardware, then it becomes much easier to process. So for example, if you see these two layouts, this is a 9 matrix multiplication. It took, for this hardware that was tested, it took 24,000 milliseconds. And if you reorder it, it had a 12 times speed up. So by simply changing on order of the loops, then you're able to speed up a number of times. And the other one is tiling. So this involves rather than computing a long loop, you can tile it into smaller loops. First, because you do not have all the memory to store all that data on chip. So you tile it so that you can avoid overwriting the data. So when you overwrite, then the meaning do not be available, then you have to get it. So that is what they call cache misses in hardware. So when we have like a large loop, we can break into smaller loops and then process it in tile sizes. So this is what we have here. Then the other technique in hardware that we use is loop unrolling. So when you have, for example, we have this inner loop in this case, so we can unroll it by a factor. So it means we can, rather than sequentially processing one of these values at a time, we can get 4 of them at the same time, perform the computation in parallel, so that in the next iteration, we are not skipping by 1, but we are skipping by 4. So this becomes very much faster. And of course, again, the other technique is using a single instruction, multiple data, as supported by some hardware. So you provide data to the hardware through various ports, and then giving a single instruction, you can perform that instruction on different data. For example, if you in a convolution, you have 3 channels or 4 channels. So on each of them, those are different data, but you can perform the same operations on at the same time. Yeah, so There are also other inference optimizations when it comes to convolution. So one of them is like converting this convolution into a format that is better, or that is more efficient than the normal nested loop of for loops. And the other one is because of some different convolution types like the depthwise, which behave differently than the standard convolution. You can also treat them differently so as we can optimize it. The other one is on memory layout. As I said, one of the challenges we have in energy especially is the order in which you are reading, how much data you are reading from external memory. So if you exploit some layout that is more efficient, then you're able to accelerate or save on some resources. So some of them I will briefly go through. For example, with the normal convolution, so we usually we take a filter and then slide it over the data, and that can be several iterations. But the other trick, this method was proposed in which you, rather than having the loops, you can basically transform this into a matrix. So you take an image and then you extrapolate it to a single field or row, and then you do a matrix multiplication. Of course, in this case, you are replicating some data, but the multiplication is much simpler than doing the convolution. So in this case, we will be having we will need an additional memory space, but maybe improving on latency. So this is one method. The other method is on some particular convolutional networks, like convolution types like the depthwise, which actually was a method that reduces the computation we need. But actually, the challenge with this method is that it has so many channels, and this can actually make it intense in terms of the activations that we need to store. So what they do, we calculate for every channel, we have a temporary buffer so that we do not write these results to the memory until we have exhausted this computation. So the way of holding data on chip until it's fully utilized, then we finally write it. So this is what this does. So, and the other one is on how we arrange or organize our data. So there are different layouts of data because really the tensor has different dimensions. So we have the search and width, then the channels, and then when we have several of these, we have n. So it matters on how you organize this data, especially on how you compute them. So from research, they have found that for pointwise convolutions, this kind of organization is much efficient. So you, rather than storing this data for every filter, you store for all the channels first, and then you move to the next, and that has proven to be more efficient than just storing it in the other layouts. So this is what it means. You store all, rather than having all this together, you will store them based on the channel dimension. So another method that was proposed that is also used in hardware is like, rather than doing this convolution in the standard way, they came up with a Winograd kind of convolution where you transform this data into a new representation, and then now it becomes a pointwise multiplication again. But now with the overhead of again transforming back to the original form. So these are just some of them. They are also good for some hardware and some more complicated than others. So, but again, it's again a trade-off when it comes to hardware design. So coming back to this demonstration. So this actually utilizes all the methods that we discussed today, where we have this NAS and also condensation performed on the model. And then we are able to deploy it on a small microcontroller with the 324 KB. So this is what they call the TinyEngine. They use an STM32 microcontroller with 16 megabytes of RAM and external 17 MB of flash. So this you can store the weights, but on the microcontroller itself, it has 324 kilobytes extra. So those are actually that's the space you have to store the activations that you produce during computations. Yeah, so they have provided this as a library that you can use to deploy any of the on any of the models you produce using this technique. So as we said, you can actually generate models from this NAS technique, and they have provided a library that you can use to deploy it on a device like this one. So for us, as an example, I will maybe show you. So this is the board. It's a very small board. So these are the development board. So it's a bit big, like its appearance here. But the small chip that has it's very small. And so it has a camera and it has a model deployed onto it. So I will maybe trying to, well, it's supposed to be running, but I think some of the okay, so here we go. So the camera is actually running. I think some of the things we have with these devices, once you touch with your hand, it introduces some static things, and then the camera stops to work. So let's see. Yeah, so maybe once we finish, when you come around, then you can see it. So it's like it's running, and so if I appear for it with good lighting, and then it's able to. I think it's a bit challenging me moving it around the floor. Probably when I can show you another demonstration, and then we will look at this stuff. Then. So this is like for objective or person detection running on this board. So you can actually do this. Like you can have small devices like this running object detection and maybe person detection. The other one that is actually new, it's like an Arduino board that is having like more of a microprocessor on chip with a microcontroller. So this one, of course, is a bit advanced than this one because it has more memory and even 3D acceleration, 3D graphics acceleration. But now I just wanted to show you that you can even set it up as a fully functioning Linux system. Let me share the screen. So it comes with examples. For example, in this case, you can classify images using you can deploy models on the hardware itself, on the hardware that has the Linux part, and then you can even deploy a web server so that you can see the results. You can even connect a camera, but in this case, I want to show you it running a small image classification, and then you can see the results on a web server. So if it's running here, so you can just drop an image, and then it will be able to detect. So this one is actually running on this device. So you can connect this at home, and you can send images, or you can have a camera, and then you can stream them to any. So I will give it an image. For example, this one. You can even change. You want to control the confidence of these models. You can run this classification, and then at this confidence, maybe it's not getting this. So you can adjust this. Because one thing with this now deployment, you actually get less confidence because you lost some accuracy in the process. So if I run again. Again, this image is also very small. I got it from, I just downloaded it from. So it's saying this is a kite. I don't know this is you, but at least it can tell that these are birds. So I can get another image.
It's a straight on ImageNet?
Yeah, this is, I think it's an ImageNet.
Okay.
Okay, this is good resolution, and probably if I have more confidence, it can. Let's say it's a sports car with a confidence of 81. So you give it some good image, and it's able to classify.
What's the resolution it's running on the input resolution?
It's in the ImageNet resolution, but now when you give it a model, it does you give it any image, it does the preprocessing.
Yes, so it will shrink it to 224 by 224.
Yeah. So you can change any image and then run it. So this is really like what they have now made it possible to have all these models run on small devices like this, and you can power them with a device, a battery. Like for this one, I'm using a power bank. You can power it with whatever thing, and that is really amazing to have all this now run on small devices. So this is maybe the exciting part, that after all this, you can deploy these models on a small device. So I think that is it for the other platforms. Maybe you can there are platforms that can enable you actually do this automatically. Let me share you. That's called, one of them is called Edge Impulse. So what this does is that you can train models. You can actually come up with a problem, collect samples of data, for example, coughing and anything, and then train a model on this platform. And then once you train the model, you can optimize it for a certain hardware, and then it will give you the real code that you can deploy to most of this hardware. So it has support for many hardware. So this is maybe something you can check. It has various applications and has accept anomaly detection, many examples.
Basically, you train your own model, then you provide them the model to train, and they're gonna optimize it for you.
So basically, a platform just click and it optimizes basically. So one of the examples that I did, for example, you can detect someone coughing, that it is a flu or something. You using the microphone, you give it some enough samples of data, give it to someone okay, and then someone sick, and you can be able to do this. So they made it quite easy to do. So there are many others. The STM, for example, STM company have also their own library. targeting their devices. I think also business for every hardware comes to their own platform. So it's very nice. Yeah, so I think that's it, and you can maybe when you pass by you can check this one. Yeah. All right, so I hope you enjoyed this, and so if you need any information, any collaboration on this TinyML things, we are glad to partner. Thank you. That's all.
So if you guys have any more questions or something, you can reach out to me on Teams or by email. And
You write it somewhere in the struggling, really struggling, but again with lighting, I guess, and we get the better. Yeah, it's doing it, but very focused.
Maybe we need to be like you can try to do it from far.
Okay, maybe that's. Okay, let's see. I think yeah, you are not a person. It was working pretty well. I think.
Where it goes.
But again, the camera they used, I think we also had a challenge because the camera they provided with the model Scala.
So this is black and white.
We tried to also use a different model of the camera, so we couldn't fix the color. So maybe this is one of the issues with this part. It was able to take some. Yeah, it can actually.
Yeah, I think we need to do it. It's one one.
Yeah, it's really able to do it, but I think the camera is the issue.
The color in the village, the right side of the so this is what lips are aimed like this.
But this one is good. Actually, you can connect.
Can't you connect this camera to this one?
You can, but then you have to like give it the not exactly, but to how to acquire the image from this to this. It's a library of fixed files. Very good. So apart from the image data, you can also have like vibrations, microphones, and there are even smaller microcontrollers from Arduino that can do these smaller models, machine learning models like KNNs that have this vibration detection and stuff. And actually, this staging bus can like help you generate code, so you don't have to write code. You give you code and then you deploy it on the.
So they provide you code.
Yeah, this one actually the example I did is provided code.
So what are the model? I thought they provided the model.
You can bring your own model, but now this was an example.
Oh, okay. So they provided the code for this example.
Yes.
Okay.
So how they have done it for the Arduino, they have provided what they call bricks, so you can detect object detection, mode detection, camera code detection, object classification. So they have provided this, and it's open source. So then you can use this as templates. Then this keyword spotting, you can actually program it so that it can spot a certain word. Say, like, for example, A3, such a thing.
Oh, activation, yeah.
But I guess in theory, you could connect the webcam, you can sample images from the webcam, right? And you can send it to the website. And then you can connect it. Do the classification on all that. Straight. Maybe.
But for this one, it's perfect because you can actually connect the hub, then camera.
Right. Okay. Then we can get it.
So because it's running Debian Linux on this.
Yeah, and you understand. You understand video for Linux device.
So it's really nice.
We have a deep learning course going on, so we created a lab for this, this week, that the students have prepared object detection model for a specific target image, like the target object, like a smartphone bug or like pen or something. And one they have to take picture using a phone, print them on the
So they do the data collection as well.
Data collection, print them, and then like deploy that model on the PC, and that's using the camera to actually deploy the demo, so show the demo in the lab. So that's the okay.
Yeah, like the end-to-end.
It's good to actually having them also do the data part, because usually that's like, and then you use this data set. And now
you get to know like how to use actually the data.
Actually, in real applications, the most challenging part is data.
Yeah, exactly.
For now, because all the models have been designed at literate. So the data is the main part, how we pre-process it and how we make sense of it. What other guys are doing for you. Just
this. So I realized I needed to show you guys, the neural affector, the genetic algorithm part, neural affector part, and then because that there was a side missing there. So I wanted to show you the genetic algorithm as well. So how the generally relations are there, but then I realized this was a different version of the presentation. Only one single slide was missing. That was not the most important one that I wanted to show. So yeah.
Well, you can send it out on
I think
on email or something, and we can at least.
it's in the GitHub repository, so it's like
Okay.
but the one I opened here is like it's better to like separate your presentation files beforehand. So I have different versions of it. So
Yeah, I have a lot of many different versions of roughly the same kind of content, but it's like tailored towards different audiences. and then and usually you update the slide slightly because maybe I have some new information, I make this a little bit nicer. And then after a while it's like, okay, so I talked for this group that long ago, so maybe it's in takes a while sometimes to find the latest slide.
So what do you think about last presentation? Were you able to get some information out of that? Or?
Yeah, maybe some part was a little bit hard to understand. There was a little bit annoying echo from the speakers that kind of was a little bit because sometimes you talk quite fast and you have the echo, and you sometimes you come almost in the bouncing between the echo and your voice, so it was a little bit hard to hear.
I felt like I was using my own mind, but when I try
I think when we're so few people, we probably don't need the speakers at all, right? But you need it for Teams, but you could probably mute the sound.
The faster to make the sound, but okay. I talk a little faster than so
I guess it depends on. So, are you from India or? Yeah. So I guess it's for you. It's your native tongue, so you can do it. I mean, probably even faster if you wanted to. But it's. I mean, if I would have grown up with Indian accent, I would probably understand it a lot better as well. But when it's fast and it's not your accent, I mean,
It becomes.
I was on exchange in Australia for a year, so if I would hear an Australian speak with that level of speed, it will probably be easier to understand things. But I mean, it's